Log on, tune in, find out. Another good idea from Cambridge.
Arnab Sen, who's going to talk about a new definition of the influence of Boolean functions.
Thank you for inviting me here. So yeah, I'm going to talk about a new definition of influences for the Boolean functions defined on the continuous product spaces. But let me just first start with defining influences in the discrete spaces, from where the motivation of this work comes from. So all I am going to say is joint work with Nathan Keller and Lincoln and Musil. Right. So let's say we have a function from the hypercube to the 2 point space 0, 1. So this is the Boolean function defined on the hypercube, and we equip this hypercube with the product Bernoulli measure. Okay, it may be biased or unbiased. So what is the influence of this function f? So the influence of the function, the influence of the jth coordinate on the function f is defined as, we compute the probability under this product measure, set of all x in the hypercube, such that if we flip the jth coordinate of x, then the corresponding value of f changes or switches. So somehow it measures how much the variable j is pivotal in determining the value of f. Okay. So this is the definition of the jth influence on this function f. And okay, so since we are only dealing with the Boolean function, so we can always identify a function with a subset of the hypercube. So I will always, if I have a subset of the hypercube, and if I want to talk about the jth influence of that subset, I always mean that this is same as the jth influence of the indicator function of that subset. So this, we always make this convention. So there are like some, so let me give 1 or 2 examples of these functions. So suppose we have majority function. So this is given by fx equal to the indicator that summation xj is greater than n over 2. Okay, and one can easily check, in this case each variable has the equal influence, and that is of the order of 1 over square root n under the, when this p equal to half. And so this is one extreme, and another extreme is the dictator function, which only depends on the one coordinate, let's say fx equal to x1, and in this case the influence of the first variable is 1 and the influence of the any other variable is 0. So this notion of influence is a central concept in discrete harmonic analysis, and it has several applications in combinatorics, let's say social choice theory, percolations, in particular noise sensitivities, and also analyzing the random k-set problems and so on. So this is a very useful concept, and actually its usefulness comes mainly from the 3 facts. Okay. So let me just describe what are those 3 facts. So first, it has a very nice geometric interpretation. So given any subset of the hypercube, the sum of the influence is, so we are talking about the uniform measure, I mean the unbiased Bernoulli measure on the hypercube for the time being. So the sum of the influences of the subset A is equal to the size of the edge boundary, that is the number of edges between A and A complement, times some normalizing constant. So this is a very nice interpretation of the sum of the influences. Okay, the second most crucial thing about the influence is the KKL bound. So actually this is the 3% Kahn, Kalai and Nilian, and they prove some non-trivial lower bound on the maximum influence of a function or a subset A in the hypercube for the uniform measure. So if you just start with this, actually if you start with the variance of f, then you can easily see that the variance of f is bounded by the sum of the influences. So this is just a standard application of f from Stein inequality, if you like. Maybe there is a constant here, but I think it's true without the constant. So this implies that that the maximum influence, maximum jth influence of any coordinate is variance of f over n. So this is the elementary lower bound on the max influence. But what KKL proved in a breakthrough paper in 1988, that they showed that this maximum influence is actually greater than or equal to some universal constant times variance of f times log n over n. So this log n is very important. So instead of 1 over n, we get log n over n. And remember that the variance of f is nothing but expectation of f times 1 minus expectation of f, because we are dealing with Boolean functions. And actually one cannot do better than this, in the sense that the dependence on n is tight. So let me show you the function. So this is called the tribe function. So it can be represented by a tree with 2 levels. So the root has let's say n over m many children, and each of its children has further m children. Okay. And each leaf is the input variable, which can take 0 or 1, and these edges are joined by and these edges are joined by or. So and if we take m equal to, let's say, log to the base 2 n over log n, approximately, maybe a small o of one term, then one can show that so basically the function outputs value depending on the value at the root. Okay. So this is the function f of x1 x2 xn. So sort of there are n over m many tribes, each containing m people. The tribes are joined by AND function, and the head of the tribes are joined by OR function. So in this example, one can show that the expectation of f is roughly of the order of roughly equal to half, and each influence is bounded by some constant times log n over n. So it shows that the dependence on n here is tight. One cannot do better. Okay. So the third usefulness of this influence theory comes from the Rousseau's lemma. So Rousseau's lemma says that suppose now we consider the before I go to the Rousseau's lemma, let me comment that so this KKL theorem holds for the uniform measure on the discrete cube here, but actually this is extended by a later paper of these three authors together with Boolean and Kadelson, which I called BKKL. Actually, in the literature, it's always called BKKL paper, and they proved it for biased measure too. So exactly the similar bound hold. And so this is a comment. So so I am talking about the Rousseau's lemma. So suppose A is a monotone set of the hypercube. By monotone I mean if we take the indicator of A, then this is a monotonically increasing or monotonically decreasing function on each of its coordinates. Now suppose let's say mu p is the Bernoulli p measure, and suppose I take monotonically increasing. Now, so this p goes to the map, the product mu p of A, this is always increasing. This is easy to see if A is increasing. Now, if we take the derivative of this map with respect to p, then we get back the sum of the influences. So actually, this proof is very easy and probably an exercise, but this is called the Rousseau's lemma. Now, why this is important? Now, assume further that A is transitive. So we assume that A is monotonically increasing, and now I assume A is transitive. Here, transitive means that so permutation group acts on the levels on the variable, right? So by transitive we mean that there is a transitive subgroup of the permutation group under which leaves the A invariant. Okay, so in that case, every variable looks like the same. So every influences of A is same, and by this KKL theorem, we know that every influence is log n over n. So their sum is of the order of log n. So we get that this derivative is of the order of log n, at least. So if the derivative of a function is going to infinity, this function looks like a step function. So that so it gives the sharp threshold result. And suppose I plot it P versus the measure of this set, then it looks like something like this, where let's say this is epsilon and this is 1 minus epsilon, and so this window, this is a result by Friedgard and Kalai. That they proved that this window is less than equal to some constant times log 1 over 2 epsilon times 1 over log n, and this 1 over log n precisely comes from the fact that this derivative is greater than equal to log n. So if we have A is monotone and transitive, we always have a sharp threshold kind of result. For example, any monotone graph property exhibits sharp threshold. So if you have a Edersonian random graph and you consider a property that it contains a triangle, or it's non-planar, or it has a Hamiltonian cycle, every such property exhibits a sharp threshold. So this is the very cute result. So now I will go to the continuous space. So with the success of this influence theory in the discrete setting, one might be tempted to extend the theory to the continuous space, but there is always this ambiguity how we define the influence for the function defined on the, let's say, general spaces, and this is not clear. So there are several existing definitions, so let me state a couple of them at least. So first is given by this BKKKL paper. So we are now working with the setting Rn, and we have a product measure mu n. So suppose I have a subset A of Rn, or a Boolean function defined on Rn equivalently. Now I define the jth influence, or they define the jth influence of A as the probability under this movement set of all x in Rn such that indicator of A xj, I am going to define what is this, is not constant. So where this axj is the one that, so the fiber of x along the direction j. So this is a one-dimensional set. So set of all y in R such that x1 up to xj minus 1, y xj plus 1 up to xn belongs to A. Okay. So this is their definition, and they proved the KKL bound holds for this definition. So we have exactly similar result, and actually this is a generalization of the discrete setting. So you can see that in the discrete setting these two definitions actually matches. So here KKL bound hold. But in the continuous setting, let's say we are talking about the Gaussian measure on Rn. This is a not quite natural definition, because you consider two functions, let's say on R2, one is this cube of side length 1 and other is this rectangle. I think that this has side length 1 and this has side length, let's say, 10. So if you consider the influence of the second variable here, then both of the function have the same influence by this definition, right? But in the Gaussian case, it is very unlikely that x2 is greater than 10 anyway. So this function actually, which is the mod x1 less than equal to 1 and mod x2 less than equal to 10, is approximately looks like mod x1 less than equal to 1, right, in the probabilistic sense, because with high probability mod x2 is going to be less than equal to 10 or maybe 100. But so the effect of x2 in this function should be small, not like this constant as of this function. So that's why this is not a natural definition. So, and then Mosel, O'Donnell and Uleskevich probably in 2010 gave another definition of this influence of this function. They call this variance influence. So we first we take the indicator function of these fibers, okay, and take the conditional variance. So this is a function of we fix all the other coordinates except the z coordinate and take the conditional variance, and then we integrate out the rest of the variables. Okay. So this definition doesn't have this problem because the variance in this direction is very small. So this is kind of a nice definition. in that sense, but again there is problem is there is no KKL bound. Okay. Now so Keller in 2010 actually also introduced as some other definition of influence, which he called H influence. So suppose H is any function, any measurable function from 0, 1 to 0, 1. Okay. Now,
can you write larger?
Sure. So H is any function from 0, 1 to 0, 1. So I take so this is I take a set A which is a subset of Rn. Now the jth H influence of A is given by the following, right? So I take the fiber Axj and then I consider its one-dimensional volume, okay, and then I apply the function H and then I integrate it out with respect to the rest of the variables. So the note that the previous two definitions are special cases of this, because in this case your H functions is nothing but, so this is 0 and 1, so H0 is 0, H1 is 0, and apart from that H is always 1. So this is this function, and in this case, in the variance influence case, Ht is t times 1 minus t. Okay, so you can see larger this the higher this H function, higher will be our influence. So we know that for this function KKL holds, but this function which lies much lower, the KKL doesn't hold. So he actually computes the boundary at up to which this KKL hold. So he showed that if Ht is greater than or equal to the entropy function, which is t log 1 over t 1 minus t log 1 minus t, then KKL holds. KKL holds with up to, like, with this constants log n over n. So somewhere, so that entropy function should be something like that. Okay, so now, but again, all of this definition lacks clear geometric interpretation, and so let me state what our definition is. So we call it the geometric influence. So we have this the A is a subset of Rn. So the jth geometric influence of A is given by, so we first compute the, instead of the computing the one dimensional measure of the set, we compute the boundary of the set, of the fiber, and we integrate it out with respect to the other variables. So this is the one dimensional boundary. So we have we inflated the set by R, subtract the measure of the original set and divide by r and take limit as r tends to 0. So limit may not exist, so we take limit. Okay, so this is our geometric influence, and this actually doesn't make much sense if this Rn doesn't have a density. The measure nu doesn't have a density, so we always assume nu has a density. So we are more interested in the Gaussian setup. So probably this definition you can take, also called Gaussian influences. Okay. So let me say now go over these 3 points. Okay, so we don't have much time. So actually, this is the geometric meaning. So if A is convex or monotone, if A is one of these, then the sum of the geometric influences of A is same as the L infinity boundary of A. So this is the as follows. We take A, we add a L infinity ball, we subtract the originals of A, divide by R, take the limit. Okay. So this is also called the boundary under uniform enlargement. So this concept of boundary is not, I think it's not too common in the literature, but actually people have interested in this and they have studied it. Actually Frank also probably have paper on it. So this is the connection. So this equality doesn't hold in general. So if you, for example, if you take q to the power n, set of all rational to the power n, you can see that this side is 0 and this side is infinity. But when A is nice, for example convex or monotone, we have this nice interpretation between boundary and the sum of the influences. And our main contribution is the KKL type bound, at least for Gaussian space. So let me just state the Gaussian case. So we proved that there exists a J such that the jth geometric influence of A, which is a subset of Rn, is greater than equal to some constant times t into 1 minus t. T is the measure of this set A, okay, and times square root of log n over n. So instead of log n, we have square root of log n over n. But actually this is sharp in the sense the dependence is tight on n. So if you take boxes, one-sided boxes, for example like this, and you choose A such a way so that the box has measure half, then you can easily check that each of the influence is of the order of square root log n over n. So you cannot do much better here. And one can also extend this Gaussian case to the case of Boltzmann measure. So the Boltzmann measure has density like e to the power minus mod x rho dx, rho is greater than equal to 1. So for rho equal to 1 we get two-sided exponential, for rho equal to 2 we get Gaussian, so on. So we have the similar bound, but now it's t into 1 minus t times log n to the power 1 minus rho divided by n. So there is a slight change in the exponent of log n. So we have, and also this is tight if you consider this kind of one-sided box example. Okay. So I don't have time to go into the proof, but let me show you one consequence of this. So we have the isoparametric inequality for this L infinity measure in the Gaussian space, which is same as the classical isoparametric inequality when you consider the Euclidean boundary in the Gaussian space. So suppose we are considering here, we are always considering the Gaussian case. So this, we know that this is greater than equal to the Gaussian isoparametric function Ht. Why? Because of course we are adding L infinity ball, so this is bigger than the L2 ball, so you always have this equality. Okay, and but this equality is tight because of these sets of the form xj less than equal to a. So this is like this is as if the isoparametric inequality for the L infinity boundary, but and one cannot do better. So this is the dimension free isoparametric inequality. But suppose I now impose the condition that our A has to be transitive, then what can we say about that? So A transitive means so A depends on all the coordinates equally in some sense. So this rules out the sets of this form, and one might guess that now the L infinity measure has to be large, and actually as a consequence of this Gaussian KKL theorem that we proved, we can show that when A is transitive, this boundary is greater than equal to some constant times t into 1 minus t times square root log n. So actually this going to infinity as n tends to infinity, unlike the classical Gaussian isoparametric inequality. Okay, and the last thing, maybe, yeah. So the last point I'm going to talk about is the Goucho's theorem. So suppose I have a nice measure nu on R with density lambda, okay, and now I can translate this measure nu by a parameter alpha, and we get a family of measures nu alpha whose density is given by lambda x minus lambda of x minus alpha. Okay, and so for example we have normal alpha comma 1, alpha belongs to real line. Now suppose A is increasing, and then we can consider the measure of this set A under this product measure nu alpha, and one can show that it is an increasing function of alpha, and actually one can easily compute its derivative, and it turns out to be the sum of the geometric influences of A. And so coupled with our, at least for the Gaussian case, coupled with our KKL type result, this implies a sharp threshold in the Gaussian space when A is increasing plus transiting. And maybe, and the window is of the order of 1 over square root log n. Now it's we find it hard to come up with a natural example where we can apply this result, but actually we can consider the following statistical problem. So suppose I have x1, x2, xn IID normal theta 1, okay, and I want to test the null hypothesis theta equal to theta naught versus the alternative hypothesis theta equal to theta 1, and I assume that theta naught is less than theta 1. And let's say beta is our some constant fixed, and beta is the maximum allowable error. So I want that whatever test I come up with, I want these two properties that under when the null hypothesis is actually true, that x1, x2, xn coming from the normal theta naught, our test reject h naught with probability less than equal to beta. This is called the level of significance, and under theta 1 our test reject h naught or accept h1 with probability at least 1 over beta. So this is our criteria, a very standard setting. Now classical Neyman-Pearson theory tells us that the most powerful test, by the way, this is called also called the power of the test. So classical Neyman-Pearson theory tells us that the most powerful test is given by based on the sufficient statistics of the data, which is the sample mean, and we reject h naught if this happens for some k, and we choose k so that our this we satisfy this thing. So this is equal to beta. So find k such that this is equal to beta. Now when does this satisfies? Now so it is very easy to see that because we know what is the distribution of this sample mean, that if theta 1 and theta naught are separated by some constant times square root n, then power is always greater than equal to 1 over beta, where this constant is depends on beta. Okay. Now suppose we may not be so lucky, and we don't have the access to the full data, but we have only access to a compressed data, which is a function of x1 to xn, and this is not in general not a sufficient statistics anymore. So there is this inefficient compression of the data, but we still want to test find a test like this, go on with testing, and suppose our k is so that this is equal to beta, and I want this condition again. Now if there is a general f, for example f is equal to identically 0, there is no hope we can make it. So we assume two conditions. One is f is monotonically increasing in each of its coordinates, and second is f is transitive. So f increasing plus transitive. So then what we can so now we ask that, okay, so for general f may not be smooth. So for general f, this may be a very weak test, but if theta 1 and theta naught are far apart, this weak test might suffice to detect and distinguish between theta 1 and theta naught. And what our theory there tells us that if theta 1 minus theta naught is some constant times square root log n, then actually this is true, that your power is greater than or equal to 1 minus beta. Okay, so this is one application, and actually this is tight. You take fx to be the max of x, and you can see that you cannot like beat this 1 over square root log n. Okay, so there is this is okay, so I have some time left, so let me state another thing. So one thing of this Gaussian measure is that it is invariant under rotation, or it's invariant under orthogonal transformation. Now, but the geometric influence depends very much on the coordinate axis, the alignment of the coordinate axis. So if I rotate a set, its measure remains the same, but your geometric influence might change very significantly. For example, suppose my set is this half space, the first coordinate is less than or equal to 0, then I know that the geometric influence of A, if we take the sum, this is of order 1, because the first coordinate is of order 1 and the rest coordinate are 0. Okay. Now I do a rotation on that, and I get a new set B, which is something like that, this subspace. So B is maybe 1 over square root 10 summation xi greater less than or equal to 0. So this subspace has the same measure, but now one can easily check that the sum of the geometric influence is at least of the order of square root n. So each of them has influence 1 over square root n. So one might, it is interesting question to ask, what is it a like a general phenomenon? And actually the answer is more or less yes. So if this is the result, so if A is convex plus some technical assumption, which is basically the boundary is smooth, so there cannot be any sharp edges along the boundary. For example, if A is bounded and A has C1 boundary, then this assumption is satisfied. Then we showed that there exists a rotation, that exists an element in the orthogonal group, such that if we rotate the body A and we compute the sum of its geometric influences, then it's greater than or equal to some constant times the ht, when ht is the Gaussian isoperimetric function, t is the measure of this set A, times square root n. And we believe that this assumption is actually not needed, but for technical reasons we need this in our proof. And of course this proof goes by like analyzing this thing for random rotation and trying to compute the expected value and show that this lower bounds hold on the expected value. Okay. So the time is more or less up. So let me just ask one question here that might be interesting. So we proved that when A is transitive, we have for the Gaussian measure, we have this bound on the L infinity boundary. In fact, this is also true for the Boltzmann measure, when instead of log n, we have then log n over 1 minus 1 over rho. Okay, so maybe it's just consider the Gaussian case. Now you fixed a t and consider set of all transitive sets which has the measure t. Now which sets achieve this minimum? So for find A in Rn such that A transitive the measure of the set is equal to t, and if we consider the, let's say, L infinity boundary of A is same as the infimum of L infinity boundary of B, and where the measure of D is again t and D is transitive. So what are those isoperimetric sets for which this happens? And so we don't know the answer. Okay, I will stop here.
Questions?
In this case over here, where you're considering rotations, can you say anything interesting about the average over all rotations?
Yeah, so actually we proved that this, actually proved the Stromer statement, right? We proved that the expectation of this over the Haar measure of orthogonal group is greater than or equal to this thing. And if you forget this assumption, we can only show that this is, I think, square root log n over square root n over square root log n. And there is this anomic log n factor which we think it should not be there. It should be true for all convex sets.
Beyond Boltzmann measures, what would be the natural things to?
So yeah, this is a good question. Actually, we thought about it. The answer is we do not know much, but so basically the proof of this KKL theorem depends heavily on the isoperimetric properties of the measure. Okay, and if we have the following kind of isoperimetric result in one dimension, so suppose my nu satisfies the following. So suppose nu has a density for me. That is a technical assumption. And the isoperimetric function of mu satisfies that it is greater than or equal to some constant times this t minimum 1 minus t log of t minimum 1 minus t to the power some constant, maybe alpha, let's say. Then our proof works. And actually this follows from, so one of your result on the L infinity boundary. So at some point of time we also need the isoperimetric result on the on Rn with respect to the infinity boundary. So, but you probably should, I think you should, that you can boost this result to the Rn. So, but so this is the level. So this we can reversely prove that there is this KKN type bound, but beyond that I don't know. What happens for the other isokinetic functions?
Okay, well, let's then speak again. Thank you.